regression lines and the contents related to regression line. Remember that after we verified that we have a basic linear correlation between two variables, and those variables have a linear correlation which is significant, the next step is to determine the equation of the line that best models the data. This line is called regression line. Sometimes it's called the line of best fit. Its equation can be used to make predictions about the y value for a given x value. Although many lines can be drawn through a set of points, a regression line is determined by specific criteria. Consider a scatter plot on your left-hand side down here. So for this scatter plot, you have some dots, right? The difference between the actual y value and the predicted y value is denoted by d sub 1. This is the very first residual. Then the next y value is located here. The predicted y value is located here. So there is a difference between them. For the third point, the actual y value and the predicted y value have another difference. Some of the differences are negative, some of the differences are positive. When you're calculating the residuals, the residual is the observed y value minus the predicted y value. So when you're working with a regression line, that regression line has a specific property. For that regression line, the sum of the squares of the residuals is minimum. For each data point, d sub I represents the difference between the observed y value and the predicted y value. As I mentioned before, if the actual y value is below the regression line, then you get a negative residual. If that y value, the observed y value, the actual y value is above the regression line, you get a positive residual. If your actual y value or observed y value is located on the line itself, then it means that, hey, the predicted y value and the actual y value have no difference and the residual is 0. So sometimes we have a positive residual, like these three cases, and sometimes we have a negative residuals, like these 3 points below the line. And again, for a regression line, we want the sum of the squares of residuals to be minimal. This is the important criteria for any regression line that best fit the data. A regression line, which also called a line of best fit, is the line for which the sum of the squares of the residuals is minimum. When it comes to algebra, we only need 2 points to graph a line passing through those 2 points. But when it comes to statistics, data science, we have many, many points. How do we find the slope and y-intercept for the regression line or line of best fit? In algebra, we have y equals to mx plus b. M is the slope of the line. In this case, it is 2 rise over run. So your rise is 2, your run is 1. So 2 divided by 1 is 2, which is the slope of the line. And the y-intercept is, in this case, 1. The line crosses y-axis, when x is equal to 0 and y is equal to 1. So when you have just 2 points, you can easily construct the equation of the line. But it's different when it comes to regression line. For the regression line or line of best fit, we have a whole different situation. You're going to use technology to basically construct the regression line. So for the equation of regression line, what is the math behind it? What is the formula that we're going to use? The equation of a regression line for an independent variable x and a dependent variable y is denoted by y hat equals to mx plus b. Y hat is the predicted y value for a given x value. The slope is denoted by m, and the y-intercept is denoted by b. To calculate m, your calculator, your software, Python, R, or any other packages that you're using follows this formula. It basically multiplies all x and y's, add them together, multiplied by n minus the summation of x values, the summation of y values divided by square x values, add them all together, multiplied by n minus the summation of all x values to the second power. So this gives you slope of the line, the rate of change. And to find b, or your y-intercept, this is y bar minus m times x bar, which is the summation of y over n. This is basically the definition of y bar, the average of y values minus m. You calculate m just right here. And then for x bar is the average of x values, the summation of x divided by n. Remember that for a regression line, the regression line always passes through the average of x and average of y. Let's take a look at one example. We want to find the equation of regression line. Let us find the equation of regression line for the gross domestic product and the carbon dioxide emissions. We represented this data before. We're going to take a look at them again. So for GDP in trillions of dollars, this is your X, free variable, independent variable, or explanatory variable. The response variable or dependent variable is y. For example, if the GDP is 1.7 trillions of dollars, then the CO2 emission is 552.6. If the GDP is 1.2 trillions of dollars, then the CO2 emission is 462.3. All of them are in millions of metric tons and so on. We visualized this before. Now our goal is to calculate m, or the slope of the line, and then find the y-intercept. We just introduced the formula for the slope of the line, and these are the calculations that we did before. It seems like the slope is 166.9, which is a positive slope. Now we're going to use this piece of information to find y-intercept. Remember that to calculate y-intercept or b, the formula is y bar minus m x bar. You already calculated m, and you're going to substitute this here. So your b is approximately y bar. Y bar is addition all of these numbers divided by 10, and x bar is the addition all of x values divided by 10. And you already calculated your m, so you're going to just substitute it for m here. Now, if you do the calculation, it is approximately 115.725. So, as you remember, this is how we visualize our scatter plot. We saw a positive correlation. We used correlation coefficient to make sure we actually have a linear correlation between the data. Now, we calculated the equation of this actual line. The equation of the line is mx plus b. And since it's a predicted value, we use a hat on top of y. Y hat is equal to m times x. Students usually forget to multiply m by x and then add b to it. Mx plus b. Since you have a line, you have a function, it has a free variable x that takes on different values. X can be 1.7, x can be 1.2, x can be 2.5, x can be any other number in between these as well. You can also use this to make predictions for the values that are not located in the table. So we calculated our regression line. What about variation? How do we explain variation about a regression line? This is another important piece of information that we need in statistics and data science. We're going to study two measures used in correlation and regression studies: the coefficient of determination and the standard error of estimate. You're going to also learn how to construct a prediction interval for y using a regression equation and a given value of x. So before studying these concepts, let us basically learn what are explained, unexplained, and total variation about regression line. To find the total variation, the explained variation, and the unexplained variation about a regression line, we must first calculate total deviation, explained deviation, and also unexplained deviation. We're going to use deviations to basically calculate variations. To calculate total deviation, this is basically the difference between the observed y value and the average y. The explained deviation is defined as the predicted y value minus the average y. And unexplained deviation is basically the difference between the actual y value and the predicted y value. So these are the basic definition of total deviation, explained deviation, and unexplained deviation. And the total deviation is the summation of the unexplained deviation and explained deviation. If you basically add these two together, the negative yi hat and positive yi hat disappear. So you get yi minus y bar. This is the distance or the difference between the point, the observed y value, and the average y value. So unexplained deviation is yi minus yi hat, and explained deviation is yi hat minus y bar. And if you add these together, you get the total deviation from the actual point to the average y bar. So we can write this way: total variation, the explained variation, and unexplained variation are all derived from total deviation, explained deviation, and explained deviation. So let's go to the next slide and define these as well. We're going to use them to introduce the idea of the coefficient of determination. The total variation about a regression line is the sum of the squares of the differences between the y value of each ordered pair and the mean of y. So for total variation, you're going to add all of these deviations that are raised to the second power. For the explained variation, the idea is the same. It's the sum of the squares of the differences between each predicted y value and the mean of y. Or you can write this way. The explained variation is the summation of the deviations between the predicted value and the average value raised to the second power. And finally, for unexplained variation, this is the summation of the squares of the differences between the y value and their predicted y value. Or we can formulate it this way. Unexplained variation is the summation of yi minus yi hat to the second power. And as we mentioned before, when you're calculating the total variation is the sum of explained variation and unexplained variation. We can write it this way as well. Total variation is explained variation plus unexplained variation. But what's the use of these? We're going to use this to introduce the idea of coefficient of determination. The coefficient of determination, or R squared, is the ratio, is a fraction of the explained variation to the total variation. You can write it this way. R squared is explained variation divided by total variation. It's important that you interpret the coefficient of determination correctly. For example, remember, we calculated the correlation coefficient to be, for example, 90%. If you have the correlation coefficient to be 90%, well, if you multiply 90% by itself, you can derive the coefficient of determination, which is 81%. What's the meaning of that? It means that 81% of the variation in y can be explained by the relationship between x and y. The remaining 19% of variation is unexplained, and it's due to other factors. Like what? Like sampling error, coincidence, or lurking variables. So only 81% of variation in y can be explained by the relationship between x and y, and the remaining 19% of variation is unexplained due to, for example, lurking variables, other variables that we haven't discussed, coincidence, or sampling error. Another important measurement is the standard error of estimate, or S sub e. S sub e, or the standard error of estimate, is the standard deviation of the observed y value about the predicted y value, which is y hat. It has a formula. S sub e, or the standard error of estimate, is the square root of the summation of the square of deviation between the observed y value minus the predicted y value divided by n minus 2. N is the number of pairs of data in your collection. And to find the standard error of estimate, these are the steps that you're going to take in words and then in symbols. First of all, you can make a table that includes the 5 columns, including xi, yi, yi hat, the predicted y value. So you need to calculate these separately, find the deviations between the actual y value and the predicted y value, and square them. After adding them all, you have the numerator of your quantity inside the square root. Use the regression equation to calculate the predicted y value. Calculate the sum of the squares divided by n minus 2 and take the square root of it. This basically gives you the standard error of estimate. Very good. Let us go over one example. We are going back to our GDP example because we already calculated a lot of important components like the regression line and so on. Remember, the regression equation for the gross domestic product and the carbon dioxide was given as y hat to be 166.9, x plus 115.725. We want to find the standard error of estimate. And let's use our table to make the necessary calculations. We need each xi. We need our yi. These are what we collected before. There is no computations for these two columns, but for the next column here, we need to calculate yi hat. So what are you going to do? You're going to plug in each xi into the formula and calculate its yi hat, which is the predicted y value. And as you can see, you have a difference between the actual y value and the predicted y value. We don't expect these to be the same values because this is a regression line equation. Now, find the difference between yi and yi hat. You're basically calculating the residuals, di. Now, calculate di squared and then add them all together. When you add all of these numbers together, this is the value that goes on the fraction on top in your numerator and is equal to 10. We found the summation of the residual squared following the formula for the standard error of estimate. S sub e is the square root of this quantity, which is your unexplained variation, divided by n minus 2, which is going to be 8, and then take the square root of it. This is our standard error of estimate. It's approximately 116.492. So the standard error of estimate of the carbon dioxide emissions for a specific gross domestic product is about 116.492. You might say, hey, it's a very large value, but you need to think about the data that you're working with. So your data are basically here 552, 462, 475, and so on, right? So comparing the data, the actual y values, and here your standard error of estimate, this number doesn't seem to be very large. Let's take a look at another example. A researcher collects the data shown at the left and conducts that. Let's take a look at the data. The radio at time, which is X, and the weekly sales, which is Y. For the radio at time is 15, and the weekly sale is 26. The radio at time is 20, the weekly sale is 32. The radio at time is 20, the weekly sale is 38. 30, 56, 40, 54, 45, 78, 50, 80, 60, 88. So it seems like we have an increasing trend here. So this researcher collects the data, and there is a significant relationship between the amount of radio advertising time in minutes per week and the weekly sales of a product in hundreds of dollars. We want to find the standard error of estimate. We want to use the regression equation. Y hat equals to 1.405 times x plus 7.311. So this is mx plus b. We want to use a table to calculate the sum of the squared differences, and then identify the number n of pairs of data, and finally calculate the standard error of estimate, or S sub e. Let us begin. In our table, we need each xi, we need each yi, we need yi hat, which can be calculated using this formula, the residual, the difference between the actual y value and the predicted y value. We also need to make those residuals squared. So let us begin. The very first x value is 15, its y value is 26. If you plug in 15 into the predicted y value, becomes 28.386. And as you can see, there is a difference between the actual y value and the predicted y value, which is negative 2.386. So it seems like this value is below the regression line. And if you square it or multiply it by itself, you get this positive number, 5.692996. You're going to repeat this process for every single value. The second x value is 20. Your y value is 32. So you have a 20. Its y value is 32. If you plug this number into the regression line, it gives you predicted value, which is 35.411. There is a difference between the actual y value and the predicted y value, which is negative 3.411. If you multiply this guy by itself, you get 11.634921. Again, you're going to repeat this process for every single x and y. You're going to take each x, plug that in to the regression line equation, and calculate its predicted value, find the difference between these two values, and then raise it to the second power. Why is that? Because we need to add all of these numbers together to basically construct a numerator. Standard error of estimate has a formula. You have the square root of the summation of yi minus yi hat to the second divided by n minus 2, which is going to be the square root of 231.967818 divided by 6. Take the square root of it, and it is about 6.218. Okay. This is a nice standard error, 6.218. So that's how we calculate the standard error of estimate manually. Now, how do we construct an interval of estimate? For the prediction intervals, remember, two variables have a bivariate normal distribution when for any fixed values of x, the corresponding values of y are normally distributed. And for any fixed values of y, the corresponding values of x are normally distributed. So here you have x1, x2, xn, and y hat is the regression line, and these are your predicted y values. This is bivariate normal distribution. Well, because the regression equations are determined using sample data, and because x and y are assumed to have a bivariate normal distribution, you can construct a prediction interval for the true value of y. Well, to construct the prediction interval, we're going to use a t-distribution with n minus 2 degrees of freedom. So again, two variables have a bivariate normal distribution when for any fixed values of x, the corresponding values of y are normally distributed. And for any fixed values of y, the corresponding values of x are also normally distributed. So let's begin. Given a linear regression equation, y hat equals to mx plus b, and x sub 0, which is a specific x value, a C prediction interval for y is y bounded between the left side by y hat minus margin of error, and on the right side, it's bounded by y hat plus margin of error. The margin of error formula is T sub C times standard error of estimate times the square root of 1 plus 1 over n plus n times the difference between that specific x value and the average x value to the second divided by n times the summation of x squared minus the summation of x to power 2. The point estimate is y hat, and the margin of error formula is given to you here. The probability that the prediction interval contains y is C, which is the level of confidence, assuming that the estimation process is repeated a large number of times. So what are the guidelines? In constructing a prediction interval for y for a specific value of x, these are the steps that we need to follow. First of all, identify the number n of pairs of data and the degrees of freedom, which is n minus 2. Next, use the regression equation and the given x value to find the point estimate y hat. Then you're going to find the critical value T sub C using the T table, find the standard error of estimate S sub E, and finally, find the margin of error to be able to form your confidence interval. Let us go over one example to feel more comfortable about this topic. Our goal is to construct a prediction interval. We're going to go back to our gross domestic product. We want to construct a 95% prediction interval for carbon dioxide emissions when the gross domestic product is 3.5 trillion. What is our conclusion? Remember that we had 10 data in our collection. So the degrees of freedom is 10 minus 2, which is 8. The regression line that we came up with was y hat, which is 166.900x plus 115.725. So in order to calculate y hat, we need to plug in 3.5 into the equation of the line. So 3.5 times 166.900 plus 115.725 gives us a predicted y value to be approximately, just showing all the algebra behind it for you, is 699.875. What's the next step? In the next step, we need to calculate the margin of error. The margin of error is T sub C times the standard error that we calculated multiplied by the square root of 1 plus 1 over n plus n times x sub 0 minus x bar to the second divided by n times the summation of x squared minus the summation of x to power 2. So T sub C is going to be 2.306. We calculated the standard error of estimate in previous slide, and we just fit the rest of the data into our calculations. Remember the T distribution table. For a 95% level of confidence and the degrees of freedom 8, remember that you had 10 data in your collection, but for the degrees of freedom, we're using 10 minus 2, which is 8. You get 2.306 as the critical value. And again, this is 95% level of confidence. So after you plug everything into the formula, the margin of error is 288.880. Remember that our y hat, the predicted y value for a specific x value, was 699.875. We calculated the margin of error. So how do we construct the confidence interval? We want to know what is the left bound, what is the right bound of our confidence interval. For any confidence interval on the left-hand side, you're going to do a subtraction. The subtraction between the y hat and the margin of error, and the right endpoint is the addition between y hat and the margin of error. So y hat minus e and y hat plus e. Left endpoint, right endpoint. The concept for confidence interval stays the same for every question. You always find your predicted value, which in this case, your point estimate, minus the margin of error that you calculated using the formula. The predicted y value, which is your point estimate, plus the margin of error. So basically on the left-hand side, the left endpoint is 410.995, and on the right side, you have 988.755. So you can basically say that, hey, my y value, I'm 95% confident that my y value is between these two numbers. We can say that, hey, we are 95% confident that when the gross domestic product is 3.5 trillions of dollars, the carbon dioxide emission will be in between 410 and 988 million metric tons. After that, you can basically form hypothesis testing and check your hypothesis as well.